Yeah.
Okay.
Thank you.
Got red, black, or blue?
So I guess today we want to have 2 speakers, right? So Yulun is not speaking.
Was I supposed to speak?
Yes.
I didn't know I agreed to that.
Because otherwise we'll move the group meeting to Friday. At least this is the email I got from Dr. Yulun.
But Friday is a brief meeting, something like.
Yes. Otherwise it will be a long meeting.
No. We need group meeting. We're meeting in Saturday, right?
Yes.
We need group meeting Friday.
Well, I told them to do it today because anybody wanted feedback for their posters, like it has to be submitted to the land people by Thursday.
Yeah.
So
Are you guys driving or flying?
Flying.
Oh, that's nice compared to last time.
You didn't drive last time. That was fun.
I did drive. I drove to Los Alamos before.
You drive alone, but we drive with Brendan and Naveen.
Yeah, I know.
We had a camping and the way. So then I'm due to show up at night at 10 p.m. The camping.
UI, are you going to talk about your poster?
I haven't finished mine.
We are.
I actually started it like an hour ago.
Okay, that's fine. So you are going to skip it?
Yeah, because I don't have it done.
Okay. So maybe Japan, you can be the first.
Okay. I guess you need to show them. So, how can I show it to here?
Don't mess it up.
Is it Polycom main or left TV?
Try both. There we go.
Okay guys, this is a very raw draft of my poster, what I'm going to present on the ESP conference. So this is the poster on the 2D nanoplate system, lead selenide 2D nanoplate system. So before going to the my whole things, I'm going to talk about, just let me tell you about why we need to look onto the system, 2D nanoplate system. Because this is lead selenide already very got a very promising applications in the, especially in the photovoltaic applications, to creating the multi-excitant generations or other applications. But using the quantum dots as the photovoltaic applications, there are some challenges like making device, or because of very reactive surface, is very hard to control the relaxation pathway and also synthesis to control this. So compared to this one is a nanoplates or 2D system is easier, is promising to using the as nanoplates because it's a 2D system, is a smooth surface. It increases the conductivity, so you can separate the hole and electrons easily. Easier than quantum dots, and also it can also change the band gap, smaller band gap, so you can use a wide spectra of the light, so and all other facilities. But problem is when you increase the dimension in it, 2D dimensions, so we don't know what is the relaxation pathway. Is it still will give you the multi-exciton generations, or is it advantageous like quantum dots or not? So we want a 2D, also good feature of the quantum dots, and also increase the introducing some new feature in the 2D nanoplates. So that's actually main motivations to doing this research 2D nanoplate system. So as I said, is one of the big challenges to synthesize one. So one of our collaborations in LANL, Dr. Kilima group, they also already able to synthesize with the control thickness to 2 nanometer thick quantum nanoplates, and they're doing this one by in a general way. They synthesize first. They synthesize the quantum dots, and then quantum dots are breezed through the lead chloride atoms, and then is propagated to the 2-dimensional. So ultimately, you will get a 2D nanoplates. And so thing is, it's very challenging to get the excited state properties by experimentally. So that's why we're doing the computational calculations. And to these calculations, we use the Tally surface swapping methods to calculate the whole everything. So I'm not going to methodology part where I was doing methodology. And this one is a published work, and how is showing that how this system was formed. Suppose like there are a small quantum dots is breezed through this green atom is a lead chloride atoms through the lead chlorides, and you will get a uniform 2D lattice, 2-dimensional lattice. And this is a result of how the surface energy, calculated binding energy of the lead chlorides and all other lead halide atoms. So it's showing that why lead chloride is favorable to create this kind of systems. So before doing this one, I took a look on the DOS, density of states. So what is the density of state? There are a lot of figures here actually. So this one is I'm comparing with the density of state in the quantum dots. These are 0-dimensional materials with 2-dimensional materials, nanoplates. And in one thing is, if you look on the total dose, this one is the total dose, this one is for nanoplates, and this one is for quantum dots. In total dose is kind of, in nanoplates also is kind of a symmetric unoccupied and occupied orbitals. So it's very similar to the quantum dots. But in case of quantum dots, since it's a 2D system, so we need to consider the different cap points and symmetry points. When I took a dispersion curve, it's showing that is a direct band gap at L symmetry point, not as a gamma point. So it's also similar to the bulk lead selenide materials. So it could be good things that it can retain some bulk lead selenide properties here. And because of that, first actually we also calculate these excited state properties at gamma point, but this result I'm showing you the calculated L point since these direct band gap L symmetry points. If we look on the projected dose, all are calculated L points. It's showing that in case of lead it's contributing mainly in the high energy unoccupied bands, and high energy occupied bands is mainly, occupied bands is mainly contribute from the selenium atoms. So one new atoms in this one is a new system in the system is lead chloride. So if you look at the chlorine, if you look at the band age doesn't contribute from the chlorine. ring is mainly contributing the very high energy, I mean, a very deep hole state, unoccupied states. So from there you can say that chlorine will interfere the relaxation pathway only if you get the very transitions from the very hot hole. If transition create the hot hole, I mean, excitement from the very deep unoccupied states. In other than, as our density of a state is very similar to the quantum dots, so we can expect that maybe relaxation pathway would be similar to the comparable to the quantum dots. And then I took a look on the absorption spectra, because absorption spectra will give us some idea about the transition types. What is the how is, and since, as I said, in the L symmetry points, they have a subgap in unoccupied state. So in here, this is very small, it's very hard to look here, but they have a subgap compared to the gamma points. Gamma point is at the gamma point is unoccupied orbital is kind of more symmetric or uniform dense, but in the alpha symmetry point is giving us there was some 4 state at the lowest state, and there was a subgap, and because of that subgap in absorption spectra is giving us a low energy band here. So this low energy band is kind of from the symmetric transition. Symmetric means is the hole and excited electron energy is almost same. So to this one in absorption spectra, I decompose these absorption spectra based on the symmetry and asymmetry. Symmetry and asymmetry means when it's exciting from the hole to the occupied state to unoccupied state, is creating one hole and also creating one electrons. So based on the electron energy means the band while it is excited to the energy difference with the frontier orbital, means LUMO orbitals, and hole energy means that the energy difference of the HOMO to the band where it is excited from. So based on the energy difference, I decompose this spectra. The solid line is showing that the symmetric transition, that means hole energy and electron energy difference, and this red line is showing that is only electron one. So if you look at here, mainly in the low energy peak is mainly coming from the symmetric transitions. In this hole and electron transition is same, energy is same, but in higher energy band, and then 2 band gap and 3 band gap type energy excitation is mainly from the asymmetric transition. And among these all asymmetric transitions, if I further decompose to the based on asymmetric electrons and asymmetric hole. Electron means hot hole, and asymmetric hole means, asymmetric electron means hot electrons. Hot electron means electron energy is higher than hole energy. And this color is very hard to see in this poster. I guess in the printed version will be better one. So the main contribution of asymmetric transition is from the hot electrons here. So in that means ion is excited at the L symmetry points at the 2 band gap or 2.5 band gap transitions are mainly creating the hot electrons. So electron energy is higher in all transitions compared to. And if we compare these things at the gamma point is more featureless compared to this one. They have no low energy band because of is a continuous band at occupied bands, and also it's showing that is a only arising from the asymmetric transition in this case. So this is similar result in case of quantum dots. Quantum dots is, if you main difference is if I look on the low energy range, still is showing that all asymmetric transition. There have no symmetric transition in this low energy range. Symmetric transition is given, is significantly at high energy ranges one. So symmetry is a whole and electron transition here. So if you look at here, is mainly almost all transitions are creating the hot holes, but which is in case of 2 nanonucleates is almost creating the more number of hot electrons in this case. So this is the main difference. And now let's look on the phonon-mediated relaxations. So this thing is, if we just briefly talk about this methodology. First, we excited to the very initial putting some initial conditions. Initial condition means we took all transitions which are creating the energy. Excited energy is around 2.5 band gaps. So the reason of getting the 2.5 band gap is there are some papers, experimental results also showing that it is more probable to create the multi-excitons when you excited at the around 2.5 band gaps. So that's why we selected that initial conditions. And these two systems are showing the 2 limiting case. First one is select all transitions which are creating the hot hole, and this one is creating the hot electrons. If we look at the excited lifetime is very longer. It's plotted up to 2.8 picosecond. But if we look at here, it didn't completely relax down to the frontal orbital. In case of electrons, it's relaxing through the 2 in very broad way, it's relaxing through the 2 bandages because this is a higher excited state and it relax to the around the subgap, and it's taking long time to relax to the frontal orbital. Because of this subgap is increasing the relaxation lifetime or decreasing the relaxation rate. In case of hole, is relaxing rate is 5, and this line is not, the average population line is not visible in here. So it's showing that how is average population is changing. In case of hole, hot hole transition it's more, I would say, faster. It's faster than hot electrons. From here, it jumped to the frontal orbital bandage one. And these results are also showing these 2 bands here. This one is showing that I separated the population and the 3 different bands. Black one is showing the initial band. So initial band is not a fixed one, it's just showing that what is the population at initially excited one. So it's at the time t equals 0, so 1 of the time is going to 0. And this red line from band A is a consist of 4 state, lowest excited state. This is, if I show the dispersion curve is out here. So in here is kind of this, around this band. So it's showing that how population is accumulating on that band. With the time is up to here, and then band 1. And green line is kind of, this range is around here. So initially it's also populating, and with the time it's retaining some, it's increasing the population, and then it started decreasing the population. That means it's relaxing to the lower excited state. And this one is for this system, and if we compare these two, we can get a result about how it's relaxing. So it's showing that electron is showing that it's not relaxed to the frontal orbital, it's relaxed to this intermediate bands because of the dispersed band gap. And then next one, these two are similar, but similar conditions, but in case of lead chloride, lead 7 quantum dot system. In case of quantum dot, it's very much, if you look, and it is relaxing smoothly and exponentially to the frontal orbital compared to this one. But the relaxation is not completed because we need to extend this trajectory. And then I look on the frequency of exciton, FFT of exciton, how is exciton energy changing. So that's better. although I did not plot the this plot from the lead selenide quantum dots. We know that lead selenide is a pure quantum dot, so lead selenide in the relaxation pathway, excited FFT on lead selenide is showing only optical modes around 150 or 150 to 250. But in this case, in case of 2D in this system and nanoplate system, beside this feature is showing there's a very long tail, I mean new frequency mode, excited frequency mode, and this excited frequency mode is arising because of introducing the lead chloride atoms. Chlorine is a lighter atoms. It introducing the new frequency modes, and we can relate with this one with these things, and that's why I'm just showing this one first, and then I can compare it with this one. And our system is a very really big system, so we did not able to calculate the normal mode. So in this case, what I did, I take the average bonding bond length with the adiabatic trajectory, and then take the front FFT of that band, or the 3 different bond, and the same. If you look at this here, it have one frequency, I mean new mode is showing for selenium chlorine bonds, and if we compare here, it's also showing a energy band and around 175 to 1 centimeter square, I mean wave number. So that means this hot hole is relaxing, is very much related to the chlorine, because of we know that is a chlorine is contributing to the higher energy occupied orbitals. So it's very reasonable that a hot hole is maybe relaxed to these phonon modes of the chlorine, subchlorine modes. And this studying this range is 150 to 200 is more composed of, if we compare to 1 here. The red line also is related to the lead chlorine, and green is a selenium chlorine. So it's mainly contributing because of this chlorine. So because of introducing the chlorine, it's showing that it's introducing the new modes, but the overall relaxation pathway is making longer. So I need to put actually more results here, so I will put it in the next version of this one. So based on all this is my conclusions. I'm not going through all of this 5. So main thing is, in case of 2D nanoplates, is showing the very different band structure at this L point. So is need to consider the symmetry points, but it's different in this case quantum dots. So, and also another thing is for relaxation pathway, because of although chlorine up there, chlorine is interfering on the very high energy hole bands, but we saw that from the observation is the main hot electrons population is more probable than hot hole. So in overall relaxation pathway is not that significantly affected by the chlorine. And another thing is creating a subgap here. Because of subgap at points is extended the excitation lifetime of the system in compared with the quantum dots. And that's all about that. And then finally is acknowledgement and all the things here. So that's all about this poster. And if you have any questions or anything you want to know more.
I'm a little bit confused about your model. So where is the lead? Where is the chlorine? It's on the surface?
No, because chlorine is a breaching atom in quantum dots, so you put the chlorine in the 12 facet, 12-1-1-0 facet. So ion is make a 2D system. 1, 2, 3, 4. Yeah, 4 edge in the middle. If you look at here, there are 4 surfaces in this side and 4 surfaces on the other side. 8 facet on the surface, and other 4 facets in vertically on the in XYZ planes. XY planes. So I would say among the 24 chlorine atoms, 16 chlorine on the surface and rest of the 8 in the middle of this plane, plates.
Why you choose this number? I mean, why you choose this concentration?
No, it's not chosen concentration. It's already proven by the experimental result and computational results. We saw that, that's why I just showed it here. This one example why we choose the 12 black chloride atoms. If we put is showing is the experimentally and by the calculations they prove that iron lead chloride has a 12-110 facet. If we put the 1 chlorine atom, 1 lead chloride atoms in each facet, and then 1 quantum dots can connect it with another quantum dots, they bind together. So it can propagate in the 2 directions. Because of that, it's just it's not arbitrary number. It's like because of the 12 facet, we need to put the 12 lead chloride on the system to make a surface. We tried the different concentrations, but different concentration doesn't give us a stable nanoplates.
What do you mean by stable?
Stable means is not able to, suppose like here, if you look at this one, this example is lead iodide. So if you look at this one and this one is made as a uniform nanoplates. And experimentally they proved that they are able to synthesize these uniform nanoplates. But in this case, it is distorted, it's not form a uniform, and thickness also is not controlled. So comparing this experimental result and our result, we can say that uniform means it's given as the lowest energy 2D system, extended system.
So you don't get a lot of defects.
Is there, not a lot of defects.
Do you need to add ligands on your system?
And they consider as a lead chloride as a ligand initially in quantum dots, but when you form nanoplates, it's kind of bridging atoms. And then they're able to synthesize in the 2 different ways. One is without any passivation on the surface, and also they are also able to synthesize on the dimethylamine passivation on the surface. So, but they say that it's not like coordinate bond with the these 2D nanoplates. So it doesn't change any photophysical properties of this one. So that's why we just consider the nanoplates one. We didn't put the name in.
So since you have lead, so do you need to include spin optical coupling in your calculations?
Yeah, but we didn't include that one here in our methodology. It's also they have a lot of approximations while we validate our methodology, but this, we cannot say that our methodology is 100% correct. Will predict the experimental result, but we can get actually some limiting case. So if we know that limiting result, we can guess what the experiment would be. Yeah, but if we include the spin orbit, it will give you the more realistic result. Yeah.
I guess because area has lots of experience, right? So for lead, it seems SOC is necessary.
So
I guess somewhat. I've seen it didn't really affect relaxation too much for just the pure quantum dot. I think it made it a little faster. I guess the thing I really need spin over for is for spin flip transitions, and you're not going to see those.
It also depends on what is the initial excitation conditions.
How about the spectral compared with experimental observation? Is it consistent?
It's energy-wise, it's not exactly consistent. I showed you in my old paper, I guess. but consistent in that sense is that in energetically in experimental one is showing that more redshifted is makes sense because because we do not include the spin orbit coupling, and we also consider the PB function also on the here also. But another thing is in overall shape at the gamma point, this kind of shape is it's a more similar feature in the experimental result.
So is lead in like the conduction band edge, or what orbitals do what contribute to?
Oh, I mean in the lowest energy one.
Or like, well, for the things I do, like lead is like the valence band edge, so it's like
yeah, lead,
so it's going to affect the band gap.
Yeah, lead is mainly contributing on the because our whole quantum dot is a lead quantum dot and lead selenide quantum dots. There are a lot of huge number of 68 lead selenide, sorry, lead atoms before adding the lead chloride. So if you look in conduction bands, conduction band is mainly arising from the lead here. But and occupied bands is mainly coming from the selenide atoms. But additional atoms is the chlorine atoms. If you look on the chlorine atoms, doesn't have any contribution on the band edge. It's contributing mainly on the the deep occupied bands.
It's not that I'm muted. On, but I turned it on.
On those graphs, what is your axis that's like representing the depth? Is that just the position on your nanoplate, or what?
So it's plotted in the adiabatic trajectory.
In the what?
Adiabatic molecular dynamics trajectory. So we created a like 2.8 femtoseconds picosecond trajectory with a 2 protein. And then this one I'm just take a random like 100, yeah, each 100 femtosecond.
Okay.
So it's showing the how band state, I mean DOS is changing with the time.
Okay.
Yeah.
Why is that helpful? I don't know. Whenever I look at those, it's just overwhelming.
It's helpful in that sense of how it's changing, because in this case it's not drastically that much changes, but we know if you look on very, I mean intensely, with the time its band gap is changing, and also like the contribution of the selenium and lead on the band edge also changing, but it's not that much high. It's kind of confirming how it's going on there. But it's not like that every time it's supposed to be like that. It could change their contribution on each orbital.
Because it looks like your total density of states looks pretty constant.
Yeah, it's pretty constant in the total density of state, almost.
So it only has like a 0.5 band gap? Half EV?
Band gap at L point is like 0.96 angstrom. In absolute number is 0.96 because it's addressed by Gaussian function. So, yeah. So now big challenge is actually, since if you look at here in like lowest energy band gap at L point, but it's can excited to the gamma point too, and then momentum conservation will become another fact to contribute here. And this relaxation is only calculated at L points, and I also calculate the relaxation at gamma points. But now challenging is like we don't know we cannot what's called discriminate the transition at the separate points. What would happen if we can include both transition at gamma and L points? So, anything else?
It's very good.
Okay, thank you guys. And
Are you going to try?
I can just tell you that everything doesn't work like it's supposed to.
so you have to be more. I will be here at around 10. Yeah.
Okay, so basically it's the same as the poster I presented at Senegal, but there is some little modifications. So my topic is computational modeling of photopolymerization reactions of cyclohexasilicon or CHS. So CHS has attracted much attention because it has been used as silicon sources to prepare silicon-containing materials like silicon nanorods, silicon quantum dots, or silicon thin film. So the preparation of silicon-containing materials using CHS follow a general chemistry. So basically, CHS undergoes ring opening polymerization because of thermal treatment of photon treatment. And with additional heat or laser, the material can undergo some bond breaking events, like the breaking of silicon-silicon bond or silicon-hydrogen bond. So this process has been captured by the experimentalist, but the corresponding theoretical study is not available. So that's the reason we want to study this system. So we would like to better understand the chemistry. So the method we use is called time-dependent excited state molecular dynamics. And our TDSMD method is different from traditional molecular dynamics. Because for traditional molecular dynamics, the system is always in the ground state. But for our method, we have a ground state as well as excited state. So basically, at first, the electrons are promoted from ground state to the excited state, and then it relaxes from excited state back to ground state. So this is called a rapid cycle. And our TDSMD calculations have many rapid cycles. And during these rapid cycles, the system accumulates kinetic energy and finally lead to photofragmentation. So here is equations for my methods. I'm going to skip it. And this is my results. So these are the configuration or snapshots along TDSMD trajectories. And the panel A and the panel D, this is the starting point for our calculations. So basically, we only consider a pair of CHS molecules, and we consider two possible placement configurations. The first one is face to face, the second one is side by side. So along the TD-SMD trajectories, we observe some chemical reactions. For example, at this specific time, we observe the ring opening leading to the formation of a dimer. And as time goes by, we can see H2 molecule is ejected from the dimer. So once we have these configurations, we can do some characterizations. So for example, here I compute the density of states for these configurations. So our finding is for the initial reactant for the pair of monomers, the band gap is pretty large. It's like 5 electron volts. So this means the molecule cannot absorb visible light, so it will be transparent stuff. So it is consistent with experimental findings. And as time goes by, along TD-SMD trajectories, we observe the decrease of the band gap. So here it's like 2.2 electron volts, but here it's like 1.8 electron volts. So we can also compute the initial spectrum. So basically what I did is I used these configurations as input for additional adiabatic molecular dynamics calculations at room temperature. And to compute the emission spectrum, we need to use this equation. So by using this equation, we assume there is instantaneous relaxation from any excitation to the lowest excited state. So in other words, we assume the emission comes from transition from LUMO to HOMO. So our observation is along TD-SMD trajectories, we observe a red shift and a line with broadening, as we can see here. So the red shift is due to the decrease of the band gap, and the broadening is actually due to the increased number of silicon H3 groups, like these groups. So this groups has a lot of freedom during thermal fluctuation. So finally, we can just get simulated mass spectrum from TD-SMD trajectories. And here I show results based on 3 different trajectories. So the dominant peak is just the monomer peak. And actually in the mass spectrum, we observe 12 features. Within each feature, we have different species corresponding to fragments with same number of silicon, but different number of hydrogens. So this one is the monomer, and here is the dimer peak. So all other fragments are due to photofragmentation at the very last stage of TD-SMD trajectories. So I guess that's it. Any questions?
What are in your mass spectrum? What are the difference between the last two? They sort of look the same. Oh, yep. Because I guess are the diagrams related to the figures on the right as well?
Yes, for these 2 trajectories, they are from simulation by using the side-by-side model as starting point. And we have different trajectories. That means different, corresponding to different photo excitations.
Is there ever 2 base peak in the third ML mass spectrum?
2 what?
Is it 2 peak or 1 peak? I'm just wondering there. The base peak in the middle.
Right here?
Is
I
it
guess
2?
it's more than 2, I guess.
What is the difference of these 2 peaks and mass difference? 1 hydrogen or?
1 hydrogen. Because at the end of TDSM trajectories, the system already accumulates very high kinetic energy. So the hydrogen atoms are very reactive.
So that means if we compare the base peak, it's almost 100%, right? 100% probability of producing a hydrogen radical. When these two peaks are, what's it called? I don't know the correct word to saying that. The intensity of this peak is the same, right? Maximum in both cases.
Not necessarily.
No, I mean here, that's what I'm saying.
No, right here I just like expand this region. So actually, the intensity is different.
Mm-hmm. Oh, okay. Number
I just
of
expanded
species,
this.
yeah. Number of species. So both have the same number of species in this. That means.
Yes.
So one is with the hydrogen radical producing, one is initial.
We are not sure if it is hydrogen radical or proton. So.
Okay.
Foresee enough for your emission. You know why one tail is longer than the other?
Right here.
CNF, so your bottom one.
Okay. So I'm assuming because for this configuration we have more ring structure, like we have 3-member ring, right? But for this one, there is no ring structure. So I assume ring structure is more stable. That means there is less thermal fluctuation during molecular dynamics calculations.
I guess that sort of makes sense. I don't know. Looking at the pictures, I thought the opposite. I thought F looked more like linear, but maybe it's just the image. And then C looks more like a cluster. So I didn't know if those had anything to do with it.
If you take a look at this silicon atom, so I guess compared to this structure, they are more easy to move, right? This coordination number of this silicon is 3, for this one is 4.
I had a question on the structure for F. So like those 3 carbons in the middle, are they like bonded into like a triangle ring, or they just? Oh, they are.
Actually, for silicon, this kind of 3-member ring is not special. It's quite common.
It's common.
Yeah. Because for carbon, it's unusual for 3-member ring. But for silicon, because silicon are much larger.
Anyone else? Once, twice.
So meeting is dismissed.
So, excuse me, I mean, how are you plotting that as an emission one here?
However,
You plot the emission one, and how this. I'm just trying to relate this equation with that your graph here.
so At each step of MD calculations, we calculate the oscillator strength. We have the energy of the problem and energy of the loop.
Oh, I didn't notice the loop.
So like at equilibrium length, you get most intense peak, and then as it stretches, like you get the
Like not straight lines.
Rogers.
Oh.
And then I went
Yeah,
Oscillation strength of which transition?
Now I'm here. I have to go drop a text.
And so it has,
grocery shopping.
so you could have lower energy and less probability to emit. So you get the high peak and the.
How to do that? I'm just living that life.
Have fun.
But did anybody write any comment on bread and one?
I haven't really read through it too much. I mean, I don't know. I've already seen this poster, I guess, a bunch of times.
I wrote like 2 things. That's it.
So many plots. Like this one, that's too many.